So yeah, we're getting about 6:03. You're feeling okay, Sean? Keep on going here. I'll just do a little chat real quick.
Yeah, let's do it.
All right, sounds good. So yeah, just like the other talks we've had, if you have questions, please feel free to throw them in the chat or the Q&A. And at the very end, sounds like Harmony already wants to meet up with Sean and Heather afterwards here sometime. We'll talk
Harmony.
about the chat and the Q&A at the very end when Sean's done. Our next talk, was going to be Jack Nisbet, and that's not going to be until January, this last Tuesday in January. We'll take December off for the holidays, and I really think that or appreciate Sean coming on an earlier Tuesday for our talks, and I appreciate all of you for showing up and taking your evening to show up for tonight's talk. Tonight, pretty excited. One of WSU's newer faculty member, I guess has been there since 2015. Time flies by pretty fast. But not far from here. He grew up in Grangeville, got his BS in math, and then figured out the light or found the light and came to geology with Idaho State and got his master's. Sounds like working with Paul Link, which is a phenomenal feat right there in its own. And then got his PhD from Princeton University in 2010 and then joined Wazoo in 2015. Super excited that we have such young, wonderful people at WSU. We had Catherine speak last year. Super fun to have her talk too.
Nice.
So without further ado, Sean Long, The Widening of the West. And I'm going to go out here and I'll sort of disappear. Thanks.
Okay. Nice. Excellent. Thanks for that intro. I'm sad I can't come up and do this in person. I was looking forward to that. But we'll have to get it in when the world rotates back to normal. But today I'm going to talk about, before I went to Wazoo, I was at, my first position was at the University of Nevada, Reno. I was there for 5 years, and I went there as a mountain belt guy. I'm done, most of what I do is working on contractional mountain belts, but I found that as a structural geologist, it was impossible to be in Nevada 5 years and not get really interested in extension. And in fact, 5 years later, extension is probably about half of what I'm working on. So, and this is just a world-class place to do it. This is the Basin and Range Province which extends down into Mexico is bar none. I don't think it has an equal in today's world in terms of being able to understand the processes that accommodate big-scale extension of continents. And also, I'm like I said, I'm dominantly a mountain belt guy by heart. So I probably view the Basin and Range a little bit differently than many people, and that's actually one of the things I want to kind of impress upon you today is that I think it's really important if we want to understand the genesis of this big, amazing province. I think it's really important to look at the starting condition, which, in other words, view it through the lens of the mountain belt that preceded it. Because as it turns, I'm going to try to emphasize that this starting condition was one of the key factors that led to ending up with such a unique province. And then, Chad, I think this info was on a email of his, but this talk I'm giving today is pretty much 100% based on the results of a paper of mine that came out in 2019 in U.S.A. Bulletin. So if you want to get a hold of this and the giant cross section, that's where to find it. And then I've worked and talked with a bunch of people that have spent either their whole career or much of their career working in the Great Basin. And, a lot of this work was inspired by a lot of conversations I've had with them, including people like Jeffrey Lee, who was until recently at Central Washington University, and he and I are working together on another project now. Chris Henry at the Nevada Bureau of Mines and Geology, who's an amazing geologist and just an encyclopedia of knowledge, particularly about volcanics. And then many others, Jim Faulds, Elizabeth Miller from Stanford, Joe Colgan, Michael Wells from UNLV, and the list goes on. There's a lot of great geologists that have been working there the last 10, 20, 30 years. So the Basin and Range is really, I mentioned before, pretty globally unique, and in that it's a huge region of continental extension. And as a result, there really, like I said, doesn't have an equal in today's world for studying the processes that dictate and govern what happens after we thicken crust. In other words, that govern the extension of the thickened crust of mountain belts. It's an amazing place to go to work on that. But it is so you might looking at the classic Basin and Range topography here, particularly through Nevada, where you see these evenly spaced mountains and valleys. You might be tempted to think that deformation was systematic and actually relatively simple, but nothing can be further from the truth. Anybody that's done field work at any scale in the Basin Range can tell you it's incredibly complicated. Normal faults are incredibly non-systematic, and many ranges have a history of multiple episodes of extension superimposed on each other. So it's quite complicated. As a result, a lot of basic questions, a lot of questions you thought may have been solved long ago are unresolved, at least at the scale that I'm interested in, including a question as basic as the strain magnitude. In other words, how much wider is the Basin and Range today than it was originally? Not an easy quantity to get at. I'm going to try to get at it with a reconstruction. And what was the distribution of this extensional strain in space and time? And if we can learn something about these two records, what do both of these two records together, how does putting both of those records together inform us about the implications for the geodynamic mechanisms that may have triggered or driven or allowed this extension to take place? Now I might be a little bit biased because I'm a structural geologist, but I would actually say that in order to even begin to investigate any of these three questions, we need a solid understanding of the basic geometric and structural framework across the province, and that would be a first step that'd be fundamental for even beginning to start answering these questions. So that's what I want to try to get at today. And I also mentioned before that I think it's incredibly important to think about it in terms of the starting condition. In other words, what the crust looked like in this region prior to all this extension. And so it happens to be the starting condition happens to be the southern portion of a mountain belt that I'm sure a lot of us watching this talk are familiar with and know and love, the North American Cordillera, which is a world-class mountain belt that runs all the way from Alaska down through Western Canada, down through the Western U.S., and even into Central America. This is a mountain belt that was constructed over a period of about 100 million years, between about 150 and 50 million years ago, from the Jurassic period into the early part of the Cenozoic. And it was dominantly constructed as a response to the development of a through-going Andean-style subduction zone up and down the entire western margin of North America. If we zoom in on the kind of the west central portion in Utah, or west central U.S. portion, in Utah, Nevada, and Northern California at the latitude that I'm going to talk about today, we can divide the Cordillera into two different main components. On the west here in red, we have the magmatic arc of the system. This is where we had a history of granitic magmatism and presumably overlying volcanism throughout the Jurassic and Cretaceous, and we constructed a huge complex of granitic batholiths. Now, to the east of the Sierras, we have this big, broad region that I'm going to refer to as the retroarc, which is, just simply refers to the area of the North American plate that was landward of the arc. And this is where all the action was happening in terms of approximately east-west directed crustal shortening. So there's a number of people that have worked and helped define a series of structural provinces, which I show here, like the Looning Fence-Maker Thrust Belt, a series of structural provinces in eastern Nevada, and then the really big one, the Severe Fold Thrust Belt over here. Calculating cumulative shortening is not that easy of a thing to do either, but we have evidence that at the minimum about 300 kilometers of east-west shortening was accommodated in this area, most of that out front here in the Severe Fold Thrust Belt. So this was really important for setting the stage for basin range extension, because the net result of all this shortening was crustal thickening, pretty significant crustal thickening. And in fact, it's given rise to the idea that the hinterland portion of the Severe Thrust Belt in eastern Nevada, mainly kind of this area I'm highlighting here, just to the west or hinterland of the frontal Severe Thrust Belt, by the end of the shortening history in the late Cretaceous and the early Paleogene, may have actually approached 50 to 60 kilometer thick crustal thicknesses. And this is based on the type of mass balance problem that I'm going to do today. And then also there's people that, there's a number of studies that have they attempted to quantify paleo elevation using a few different proxies. And a lot of these come up with usually between about 2.5 to even 3.5 locally kilometer elevation estimates in the earliest tertiary, after shortening it had completed. So this has given rise to this idea of Nevada Plano, which is a name that arose due to comparison to the modern day Altiplano in South America, in Bolivia and Peru. So 3 kilometers elevation is not quite as high as the 4 kilometer high Altiplano, but it's still pretty significant. And then finally, I want to talk about 2 other events that are really important and kind of set the stage for basin range extension. One would be that between about 65 or after about 65 million years ago, when we kind of shut off shortening in the severe thrust belt at this latitude, we had an eastward shift or eastward transition of magnetism and deformation that migrated into kind of eastern Utah and Colorado at this latitude, and they constructed what we know today as the Laramide province. This surface record has been interpreted by several to represent the record of shallowing of the angle of the subducting Farallon slab, shifting deformation and magnetism eastward. But then even more important and more relevant for the Basin and Range, immediately following this was a very important event in the Great Basin. Between about 45 and 25 million years ago, kind of smack dab in the middle of the Cenozoic, we had a really well-documented northeast, starting kind of up here by Elko, to southwest sweep of explosive silicic volcanism. We call this event the Great Basin ignimbrite flare-up. And this kind of time-transgressive sweep toward the south has been interpreted. This surface record has been interpreted to represent perhaps the steepening or rollback of this subducting Farallon slab to a dip angle similar to what it had before when the Sierra Nevada magmatic arc was constructed. But this ends up being a really important event for the Basin and Range, and I'll explain why here in a second. So diving into kind of the new contribution I want to try to make is the goals I have are I want to illustrate the geometry, the structural geometry at a province-wide scale, and attempt to quantify the magnitude of extension across the central part of the Basin Range at about 39 degrees north latitude, which essentially runs from just south of Reno over through eastern Nevada, where Highway 50 goes through. If you've ever been on that highway, it's a really cool highway. That's the loneliest highway in America. And the tool I want to use to get at this is a classical tool of structural geology, which is the cross-section, right? So anybody who's taken structure or taken field camp, I'm sure you've drawn cross-sections before. But if they're drawn rigorously and in a way that we can retrodeform them, they can be a pretty powerful tool to actually put numbers on the amount of extension that's happened or the amount of shortening that's happened. So I want to integrate this cross-section restoration with recently published crustal thickness data, MOHO depth data across the Great Basin at this latitude from the EarthScope program, in order to so again, I'm a mountain belt guy at heart, so I'm really interested in what the mountain belt looked like prior to extension. So I want to integrate this reconstruction with modern day crustal thicknesses in order to attempt to put some constraints on the thickness magnitude of the crust in the Cordillera that predated extension. And also, something that's been on my mind and a lot of other people's minds quite a while is one of the amazing things about the Basin Range is that it does not have a homogeneous distribution of extensional strain. Some places have been extended by 100, 200%, and they're right next to places that have been extended by 5, 10, or 15%. And it's quite confusing, and I've always wondered, is there a systematic reason for that? Can we attempt to explain why that happens? So I'm going to attempt to address that today as well. And then finally, I don't collect any new timing constraints, but but I made a pretty thorough compilation of published timing constraints within about 100 kilometers north and south of the section lines. So I want to integrate the reconstruction with timing constraints in order to try to place extension in the context of the events that were happening at the either intraplate scale or interplate scale over this period of time that may have helped facilitate or drive or allow extension to take place. So here's the first view of the big cross section. So just as a disclaimer, this thing is really big. It's physically very big. It's published at 1 to 200,000 in the U.S.A. Bulletin thing, but even at that scale, it's about 12 feet wide. And so it does not translate well to a PowerPoint slide at all. But we will be looking at we're going to be kind of going through range by range and look at some detailed ranges here. So, but But the method I used was I figured the only way to address this problem was to dig into the detailed structural geometry on a range by range scale across the entire province. And so I dug into published geologic maps that were pretty detailed. So I found 36 different map sources that were useful that were between about 1 to 24 and 1 to 62,000 scale. So pretty detailed mapping with lots of measurements. And I used these to draft new cross sections of 18 different ranges that span from just south of Lake Tahoe all the way over to Delta, Utah. And then over here, this big section on the east, I actually used the published cross-section through the severe fold thrust belt of Pete DeSalle and Jim Coogan that was published back in 2006. But to the west of there, as we move west, these are my 18 new sections of each range. This, again, incidentally, what I'm looking at here, this top part of the section is the modern-day geometry. And down here is the geometry after restoration, where everything's been scooted closer together. Also, for your reference, this gray stuff that's kind of hard to see at this scale down here. This is annotation of the 1980s CoCorp seismic profile across actually what ends up being slightly north of my section line. And then these gray bars are actually MOHO depths from seismic stations of the EarthScope program. So a note on the section line. So, right, normally, ideally, we would draw one east-west section line across the entire basin and range, but the lines of section, actually, you'll see they don't line up in an east-west line. There's an important reason for that. One is we don't have detailed mapping everywhere, right? So we need detailed quality mapping to support each one of these sections. But they were also drawn to optimize a number of other factors, including one, trying to definitely get quality, well-mapped, well-determined exposures of major normal fault systems. In other words, so we can determine their offset, magnitude, and geometry. And then also, particularly in eastern Nevada, I selected the section lines so they also cross the axes of Mesozoic thrust faults and folds, because I'm really interested in learning about the geometry of contraction that predated all this extension. But the single most important reason for choosing these section lines had to do with the ability to retro-deform the cross-sections. And so what I mean by that is each one of these section lines was chosen so it maximizes the number of across-strike exposures of a really important contact. And in fact, it's an unconformity. It's an erosion surface that's present across the entire basin range. And this is what I'm going to refer to as the Paleogene subvolcanic unconformity. And this is really the key to being able to retro-deform our sections. And so I'll explain why here. So I mentioned the Great Basin ignimbrite flare-up before. It was this northeast to southwest sweep from about 40 to 45 MA up here down to maybe about 25 at the southern latitude of where I worked. It was this sweep of explosive silicic volcanism that blanketed much of eastern Nevada, or blanketed pretty much the whole state of Nevada and parts of western Utah with a variable thickness of tuffs and locally lavas. So the reason it's so important structurally is because of what underlies it. So the basal unconformity, which varies between about 40 and 25 million years old, is present across the entire Great Basin. And at a really big scale, it approximates a subhorizontal datum. And that ends up being really important because this unconformity could not have come at a better time. It postdates, almost immediately postdates the contractional deformation, in other words, the thrust faulting and folding that built the Cordillera mountain belt. So it postdates contractional mountain building. And it, in 98+% of places, it predates extension. There's a few places where extension is before volcanism, but that's very rare. So it ends up being an incredibly important piece of information. It actually ends up being, really, in my opinion, the Rosetta Stone for being able to restore extension quantitatively in these ranges. Because as we all know, normal faults accommodate displacement, right? They drop the hanging wall relative to the footwall, but that's really only one of two things they do. They accommodate displacement, and they also accommodate horizontal axis rotation. In other words, rotation of big crustal blocks. And it's that component that's a little harder to get at. But this is where the unconformity comes in, because I know the unconformity was a subhorizontal datum prior to extension, just about everywhere. This allows us to quantify how much rotation we undo. So, for example, this is a highly extended range called the Wasatch Range in western Nevada, And, you can see a series of big normal faults that are, that drop the hanging wall relative to the footwall. And the normal faults today are pretty flat, but they have highly, this thick red line is the Paleogene unconformity, and there's volcanics above it. And we know that before extension, they're dipping about 50, 60 degrees to the west today. So we know that before extension, we have to unrotate all these blocks up about 50 degrees. And that's critical info that we need to know to be able to restore a section through a range. So I can just walk you through an example of how I restore one of these sections, or the kind of the retro deformation exercise. So looking at the U.S.A range again. So first, well, step one, I have to draft the section in a way that it's internally consistent, meaning that every feature that's offset by a normal fault has been offset by the same amount. And therefore, when I unslip the normal fault, all those features match up. So that's step one. But, first, we take the modern geometry and we restore offset on normal faults. So I'm going to unslip this big normal fault, shove that block up until the unconformity matches up again. And so down here, we've undone all the slip on normal faults. And then we've undone or retro-deformed the amount of tilting recorded by this Paleogene unconformity, which again, in all the section lines is going to be this dark red line. And so we untilt it until it's horizontal, because we know that it approximated a sub-horizontal datum prior to all this extension. And then we do the classical method of structural geology, which is simply comparing the modern day length, east-west length of the range, to the restored east-west length of the range. And we compare those initial and final widths, and to calculate extension. And we can either calculate it as an absolute number in terms of kilometers, or we can calculate it as a percentage. Either way. And then here's another example. So this is the White Pine Range in eastern Nevada, and it hasn't been extended very much. You can see that there's a few relatively modest offset normal faults. And there's the Paleogene unconformity is located here, here, and here, and it's barely tilted at all. So down here, when we retro-deform extension, we only get about 13%. It's not much wider than it was originally. But one cool thing that comes out of it is since I draft my sections above and below the erosion surface where possible, we get information on the geometry of big-scale folds and thrust faults of the Cordillera and Mountain Belt. So there's a lot that falls out of this process. So a little note on the modern basins, right? So there's no east-west line that we can draw across the Basin and Range Province that's going to have 100% bedrock exposure, right? Because we have the classic Basin and Range topography of alternating extended bedrock exposed in ranges, and then in between ranges, we have these regularly spaced valleys that have been accumulating sediment for most of, from the middle Miocene to the present. So we don't have 100% bedrock exposure, and we don't even remotely have the kind of subsurface data that we would need to estimate, let alone to even estimate the geometry of the half-graben and the geometry of the basal unconformity in those ranges, let alone what went on with normal faults underneath that unconformity. So the basins are tough. We can't really, and as a result, I didn't really even attempt to illustrate the geometry. I just focused on, I didn't attempt to illustrate the geometry of what was going on in the ranges because, again, we don't have enough information available. But what I did is I actually did incorporate them into the retro deformation process. And I took what I considered to be as simple of an approach as I could think of, which is I assumed that the amount that I closed this basin east-west in the restoration is best approximated by the magnitude of extension recorded in the ranges on either side. So in other words, this range right here was extended about 180%. This range was extended about 180%. So the intervening valley I closed by that magnitude in the restoration. And then I would calculate an uncertainty that was based on the difference in percent extension between these two ranges. So in this case, it ended up being a low uncertainty because the two ranges were similar in percent extension magnitude. But for example, for this valley over here, this range was extended 20% and this range was extended 180%. So the corresponding uncertainty of closing that valley ended up being a little higher. So again, this is as simple of an approach as I could think of. And, the big underlying question is this a good approximation for how much these basins got opened? My answer would be not everywhere, honestly. I think this method would do an okay job in the areas where the ranges themselves have been really strongly extended, and therefore that the amount of extra opening in the valleys is probably minimal compared to that. However, I think this technique probably underestimates extension in areas where the bedrock and the ranges themselves has not been highly extended, because in that case, a big range bounding fault might be the biggest fault in the whole system, and we're not able to nail down slip on it. So that's one of a few caveats I want to put forward here, because this is a big, wide province, and there's a lot of areas of non-exposure. So there's a lot of we want to be cautious when we interpret a reconstruction like this. So here's a few caveats. One is, it's kind of a classical procedure in structure, whether you're drafting a contractional cross-section or extensional one, to try to minimize the amount of strain it takes to produce the geometries you see. So drafting decisions were always sought to minimize the amount of extension necessary. At the scale I worked at, faults that had less than about 100 meters of offset weren't realistic to include. So it doesn't include small-scale faults. And again, I think the method that I used for closing the basins probably underestimates extension in areas where the ranges themselves have not been extended very much. So all of this is to say that I think this province-wide estimate that I came up with is likely conservative. It's likely a minimum value. And the error that I calculated is also likely conservative as well. Right? So it's important to acknowledge there's unknowns here. So let's. What I want to do is we're not going to look at every single range, but we're going to march from east to west and talk about some notable ones. So for one, on the very east, this would be westernmost Utah. The beginning of the Colorado Plateau would be right about here. This is the modern day geometry and restored geometry from the Pete DeSalle and Jim Coogan cross-section of 2006. And it's beautiful. It beautifully illustrates the geometry of the severe fold thrust belt, which is an incredible structural province that accommodated over 200 kilometers of east-west shortening, dominantly over the Cretaceous. And so, we can see that beautiful thrust geometry here. But that's a story for another time. What I want to get at today is how much it's been extended. So if we look at the frontal part, it actually has not been extended very much. But one interesting thing we see a few half grabens at the surface. But notice what's controlling these half grabens. We had a series of thrust faults that were ramping up to the surface, and we simply backslid these thrust ramps to form gently dipping half grabens. So this is a really cool example of the pre-extensional geometry of contractional deformation, exerting a really strong control on where and how much extension we got. Now, as we move further west, we come to the canyon. So anyway, the frontal part of the severe thrust belt was only extended about 10%. But as we move further to the west, we come across one of what are going to be two pretty big low-angle detachment faults that we're going to see on our way. This one's called the severe desert detachment. It's on DeSalle's cross-section between points in the hanging wall and footwall. It's estimated it accounts for about 45 kilometers of top down to the west displacement on a relatively gently west dipping contact. Again, though, when we look at the restored extension or the restored section versus the modern section, you can clearly see a really strong influence of pre-existing thrust geometry in that the severe desert detachment looks like it's essentially reactivating and backslipping along that gently west-dipping ramp that was essentially the primary western root zone of the severe fold thrust belt. So this ends up demarcating the beginning of what's going to be a big, broad, wide province of pretty high magnitude extension that extends all the way into eastern Nevada. So let's go, all the way to central Nevada. Let's march our way west. So when we cross the Nevada-Utah border, we enter the most complicated and most controversial range of the entire transect, which is the Northern Snake Range. This is right north of Great Basin National Park, and this is one of our two big metamorphic or Cordillera and metamorphic core complexes. And I'm working here now. I have a new project here now, and it is spectacular. It's if you're a structure nerd like me, it doesn't come much better than this. So this is the only range on the entire transect to exhume ductily deformed rocks. So in other words, it's the only one to exhume rocks that were instead of being brittly broken by normal faults, they were penetratively stretched and thinned down at mid-crustal levels. This is the only range to exhume rocks from mid-crustal levels. Now, there's been a lot of people that have worked on the Snake Range since about the 70s, and there's been kind of a long-standing controversy over the amount of offset on the primary extensional structure of the range, which I'm kind of highlighting here. It's called the Northern Snake Range décollement. It's actually, there's no features we can match up between the hanging wall and footwall that allow us to nail down offset. But we can look at the amount, of extension accommodated on this section line. which I was able to get a crude minimum estimate by looking at all these blocks that are stranded and preserved above the décollement, and essentially shoving. What I did here was I shoved those back together as close as I could without them overlapping. It's the simplest way I could think to do it. And from this, I get a minimum of about 125% extension. So, right, it's over almost 2.5 times as wide as it was originally. And then Jeff Lee, remember he was at Central Washington University. He did his PhD here, and he did a really cool study in the 80s where he quantified the amount of ductile stretching in the footwall of the décollement, estimated about 250%. So really highly extended. And again, so this is neat. This modern and this deformed, these are shown at the same scale. So this is kind of cool. There's so much east to west widening here. But neither of these quantities actually gets us at the amount of slip on the décollement, because again, we don't have any features to match up across it. And fortunately, there's been a number of models that have come out over the years. However, the downside is they range from not that much displacement to quite a bit. They range from about as low as 15 to as high as about 45. And so what I did, in an effort to make everyone happy, and the fact that this is a really difficult problem to get at, I essentially I incorporated the low and high range of offset magnitudes into the reconstruction and presented it as a center value and error, 30 plus or minus 14 kilometers. This ends up being the largest single source of uncertainty in the restoration. So stay tuned, though. I'm actually, in the next couple of years, I'm hoping to really tackle this problem with some by looking at the surrounding ranges. It's really a neat place. And now, as we move further west, we get to my favorite, I think the most scenic area of Nevada, which is the area of right along Highway 50 between the glorious towns of Eureka and Ely. If you haven't been there, it's a pretty amazing place. So what we see here is a series of about 5 or 6 ranges, including the Shell Creek Range, the Egan Range, the White Pine Range, the Pancake Range, that have actually, many of them have been pretty highly extended, up to about 70 to 80% extension in individual ranges. But one cool thing is when we retrodeform extension here, this highlights the existence of really big scale folds that were formed during the Cordillera Mountain Belt, such as this one right here, which was had about a 5 kilometer amplitude and it was about 20 kilometers wide, and folds over here of comparable scale. This fold right here is called the Butte Synclinorium. You can trace this fold in and out of the page for 300 kilometers. So these folds are big scale Cordilleran features that go well in and out of the page. So they're big structures. Now I want to talk about this range for a second, because there's something very unique and interesting going on in this range. This happened to have been the first place that I worked when I went to Nevada. This is the Diamond Mountains and the Fish Creek Range near the small mining town of Eureka. And the thing that's unique going on here is this is the only range in the entire transect to exhibit normal faults that actually are older than mid-tertiary volcanism. So and there's a number of them. There's 4 or 5 or 6 of them. For example, this big down to the west normal fault has about 5 kilometers of slip on it. And all of that slip predates this red line, which is about a 37 million year old unconformity. Not only does the slip predate it, but we also eroded the entire footwall down before volcanism. So this is the only range in the entire transect to exhibit pre-volcanic extension. And naturally, it's about work I did about 4 or 5 years ago. I was really interested in the timing of extension. So what I did was I utilized low temperature thermochronology from these kind of deeply zoomed Cambrian quartzites here. Found a really rapid history of cooling between about 75 and 60 MA that brought these much closer to the surface. And we interpreted that as the best estimate for the timing of extension. Now, that's interesting one of the reasons that's interesting is because, well, this is highlighting a really interesting regional story of the growth and subsequent extensional collapse of a big anticline that we call the Eureka culmination. And the thing that's interesting to think about that is this extension was going on while the severe thrust belt was still active, while it was still accommodating displacement, making it what we call synorogenic extension. So we'll talk a little bit about the end of the talk about what that means. But suffice it to say, this is the only range on the entire east-west transect where we see any evidence for any extension predating this mid-tertiary volcanism. So it's the only significant pre-volcanic extension on the section line. Now, as we move further west, there's 4 ranges in west central Nevada that all exhibit pretty low extension magnitudes, usually about 5 to 10 to 15%. And the corresponding tilting of the Paleogene unconformity is very gentle, usually less than about 10 degrees. So it's kind of a province of low magnitude extension in western Nevada, or in kind of west central Nevada. Now, as we get all the way to the very western end, we get really high magnitude extension. In fact, up to 180% extension in 3 of the 6 westernmost ranges. And this extension in all 6 of these ranges happened by a very systematic and interesting style that we refer to as domino style extension, which is just like it sounds. Imagine we had a bunch of books on a bookshelf, and the faults started out at a high angle, and they represent the contacts between the books. Then imagine we take the book stop away, all the books rotate over. Well, the faults are simply accommodating rotation of the blocks between them. And the faults start out high angle and rotate to progressively lower angles, while the rocks that they carry rotate to progressively higher angles. We see this style, this kind of rather homogeneous style in all 6 of these western ranges. And in fact, the range where this style was originally defined is right here. This is near the town of Yerington, Nevada. This is the Singati Range. This is where Prophet in 1977 first kind of documented this style. So these big normal faults have 4, 5, 6 kilometers of slip on them, and the normal faults today are pretty much flat. But they have cutoff angles of about 60 degrees with these volcanics, and the Paleogene unconformity at the base of the volcanics is tilted about 60 degrees, which tells us that these unrotate to a steep geometry, a steep initial dip angle. And then a couple other interesting things going on here. So right over here is the Sierra Nevada mountains proper. This is just south of Lake Tahoe. But notice, this is the Sierra Nevada mountains proper. But notice this range, this one, and this one are all dominated by red bedrock. Well, that red bedrock is Jurassic to Cretaceous granite of the Sierra Nevada magmatic arc system, meaning that the westernmost 4 or even 5 ranges of the Basin and Range that were complexly extended actually extended pretty much the eastern half of the magmatic arc. So it's interesting, because I always thought, that, the Sierra Nevada granites are up in the Sierra Nevada mountains. But actually, they extend a long way to the east into the westernmost 4 ranges of the Basin and Range at this latitude. Finally, one other interesting thing paleogeographically is, so notice here's the Paleogene unconformity sitting on top of these exhumed Jurassic Cretaceous granites. And over the top of that, in the kind of starting in the early to middle Miocene, we start emplacing about up to 3 kilometers of tuffs and a lot of intermediate lavas that we refer to as the ancestral Cascades volcanoes or volcanic arc system. So this is pretty neat. We are actually, right? So we, all through the Jurassic Cretaceous, we had pretty steep subduction, and we were building this giant granitic arc, a magmatic arc above it. Then during the Laramide event, we translate magmatism way to the east, and we kind of uplift and erode all these granites. Then the slab rolls back, and by the early Miocene, we construct a Miocene volcanic arc on top of the exhumed guts of a Jurassic to Cretaceous magmatic arc. So paleogeographically, that's pretty interesting, I think. The slab rolled back to essentially its same dip angle it had before. All right, I know you've been on the edge of your seats trying to figure out how much extension went on here, right? So finally, I'm not going to keep you waiting any longer. Let's look at the results of the restoration exercise. So when we measure from the westernmost normal fault in the Sierra Nevadas to the easternmost normal fault over here on the western edge of the Colorado Plateau, the final east-west length of this province is 734 kilometers. And when we restore extension, including the semi-quantitative way I've restored valleys, we get an original length of 504 kilometers. That corresponds to drum roll please, a total extension magnitude of 230 kilometers. But the real important value here is that ends up being almost 50%. In other words, Nevada and Utah are about 1.5 times wider than they were originally. And maybe that was a bit less than you might have thought. But remember, this is a minimum estimate. This is the minimum amount, I would say, required by the geologic record. And then much of this uncertainty, I have 42 kilometers of uncertainty. I would definitely consider that a minimum. Much of this uncertainty had to do with how I closed the basins and the uncertainty in how we restore the northern snake range to Coleman. But let's run with this from here and start talking about implications of this restoration for the Cordillera and mountain belt. So what I want to do is I want to integrate this restoration with MOHO depths from proximal seismic stations that are really close to my section lines that are from the EarthScope program. They're kind of hard to see, but here's my section. Those MOHO depths are these gray lines shown down here. These are the depths of the MOHO for the EarthScope program. And so they're also listed down here in terms of depth. Now we can if we just simply pretend that the entire retroarc we can calculate an average, and actually that average isn't too far off. The average modern thickness is about 37 kilometers across the Basin and Range at this latitude, and it doesn't really vary all that much except in a couple places. So if we treat the entire retroarc or the entire Basin and Range and pretend it just had a uniform modern thickness like this, which would be this red box I highlight here, we can squish everything back together and just do a simple rectangle mass balance problem. And doing that exercise tells us that we have enough crust preserved in the Basin Range today to account for a 54-kilometer average thickness of crust across the entire Cordillera and mountain belt. But again, so this relies on, again, a simplified assumption that the ductile middle and lower crust are being homogeneously stretched and thinned by an equivalent magnitude to the brittle extension recorded in the upper crust. And it also, of course, is just, we're simplifying the entire Cordillera mountain belt into one average thickness. So we have enough crust to account for a 54-kilometer average thickness across the Cordillera mountain belt. Now, I think we can take this a step further, though, because one of the other questions I want to try to get at is, okay, why do we get a bunch of extension in parts of the Basin Range and less in others? And actually, one of the things that really jumped out at me when I did this exercise was that there are 4 domains that really jumped out. There was 2 very distinct high magnitude domains that had about 60 to 70% average extension, separated by 2 low domains that were only about 10%. Now, again, if we make this simplified assumption that the middle and lower crust immediately beneath underwent the same amount of stretching and thinning as the brittle extension recorded in the overlying upper crust, this implies that the possibility for differences in pre-extensional thickness within the Cordillera and mountain belt itself, which is something that interests me a lot. So first, let's look at these domains. Domain 1 here on the east side is adjacent to the Colorado. This is the frontal part of the severe thrust belt adjacent to the Colorado Plateau. Only had about 10% extension, and it restores to about 40 kilometers thick, which is a similar thickness to the Colorado Plateau crust next to it today. Finally, we move just west of that. We get this big, broad region of westernmost Utah and eastern Nevada that had high magnitude extension, about 66% average. It restores to about 60 kilometers thick. Domain 3, there was these 4 ranges in west central Nevada that had very low magnitude extension. It restores to about 41 kilometers thick. And then finally, our second big domain on the western end, a domain of high magnitude extension in western Nevada, had about 60% average extension, and it would restore to about 66 kilometers thick. So again, this is a very simplified reconstruction. A more important question would be, is there any geologic reason to think that parts of the Cordillera would have had thicker crust than others? And so from this, we have to use a whole different line of reasoning. And I'm going to put forth the case that there is, and I want to talk about what I think were the dominant thickening mechanisms in different parts of the Cordillera at this latitude. In fact, I want to try to make a case that these 2 domains, or that the areas of the Cordillera and mountain belt that likely, for a couple reasons, had the thickest crust, consequently were extended the most. Here's what I want to attempt to put forth some arguments here. So first off, the eastern domain, focusing on this eastern domain first, the eastern domain consists of the westernmost couple ranges in Utah all the way across eastern Nevada, about to the town of Eureka. So this is where paleoaltimetry predicts that we would have had the high elevation retroarc plateau. Now the question is, what would be the dominant thickening mechanism out here, and why would you get thicker crust here than elsewhere? Well, because the interesting thing is, right, so we have the Whopper severe thrust belt out here, but actually the frontal part of the severe thrust belt wasn't extended that much. And once we move to the west, people like myself and a few others that have looked at thrust belts in eastern Nevada, we can't account for very much lateral shortening or thickening. So what would have been the mechanism by which we could thicken the crust of eastern Nevada? Well, this is something I've been talking about for a couple of years. In order to understand this, we've got to go back in time to the Neoproterozoic, 600 million years ago, when we were rifting the western edge of the North American continent and opening what was to be the ancestral Pacific. What we did was we created a long-standing feature called the Wasatch Hinge Line, which is interpreted to demarcate the western limit of rifting of thick North American continental crust. West of the Wasatch Hinge Line, we see an almost order of magnitude increase in the thickness of the Neoproterozoic to Mesozoic passive margin basin. It's nearly 15, even approaching 20 kilometers thick in Nevada. As opposed to east of the hinge line, we have the thin cratonic section that you see in the Grand Canyon. So fast forward to the severe mountain building event over most of the Cretaceous, we accommodated in excess of 220 kilometers of east-west shortening in the severe fold thrust belt right here. So we have to think about what that implies for what's going on in the lower middle crust. So essentially, what we did during the Cordillera mountain belt was we detached, or when we constructed the severe thrust belt, we essentially detached and translated eastward the entire 15 to 20 kilometer thick passive margin basin up and over an equivalent east-west length of unrifted, thick North American crust that would have originally lay east of the hinge line, but has now essentially been inserted or shoved underneath Nevada. So another way to say this was that we underthrust a 220 kilometer minimum east-west width of thick, likely 40 kilometer thick, unrifted North American craton westward underneath eastern Nevada, which I've interpreted for a while as likely the dominant thickening mechanism. This is a way to add up to 15 or perhaps more kilometers of crust to the crustal column without internal deformation. Now, interestingly, when we account for the 220 kilometers of shortening in the severe thrust belt, that puts the western edge of the underthrusted position of the Wasatch Hinge Line at about the western edge of the zone of high magnitude extension. Now, that was a mouthful, but the western high magnitude extension domain is much easier to explain. It coincides with the eastern half of the Sierra magmatic arc and the proximal Looning Fence-Maker thrust belt, which is very high strain. The dominant thickening mechanism here would be construction of the enormous complex, both of the upper crust and mafic residues or left behind melt residues in the lower crust, constructing this gigantic magmatic arc system, which xenolith studies have suggested likely approach thicknesses of up to 70 kilometers prior to later delamination. So construction of the Sierra Nevada magmatic arc would be the dominant thickening mechanism out there. So what I'm trying to make the case is I feel there's actually a couple important structural reasons why we may have had portions of the Cordillera that had quite a bit thicker crust than others, and that these were the principal control on the amount of extensional strain that we got in the basin and range. In other words, the areas that were extended the most were extending the most because they were trying to even out gradients in crustal thickness. That's the argument I'm trying to make here. So I have one last thing I want to do, and this shouldn't take too long. I don't want to, what this is a compilation of timing constraints. And none of these are mine. These are, well, a few of them are actually, but most of them are. These are about 60 studies that I compiled that are all within about 100 kilometers north or south of each of these section lines. And the goal of this graph, of this exercise, is I want to attempt to place extension in a temporal framework so we can attempt to explore the geodynamic driving mechanisms that may have allowed episodes of extension to take place. So I'm not going to get too deep into this graph, but this graph is a graph of time on the vertical axis from the modern day up here all the way down to the Cretaceous. And west is longitude on this axis with west. Oh, here's the California-Nevada border here. Here's the Nevada-Utah border. So west on this side, east on this side. And I graph a bunch of constraints that are based either on low temperature thermochronology in green, geochronology of pre-syn or post-extensional volcanic rocks in red, and geochronology of syn-extensional sedimentary rocks in brown. So a couple key time horizons would be right around here, about 65 MA was when the severe thrust belt shut off. This line represents the initial, the first ignimbrite flare-up magmatism to show up on the section line, which gets systematically younger toward the west. And this line at about 17 MA represents a foundational episode in the growth and development of the San Andreas transform outboard of all this. So rather than get bogged down in study to study, I want to highlight a couple key patterns, which is a significant difference between the high magnitude extension in the retroarc plateau in the east, which is highlighted over here, which illustrates a rather protracted history from extension as early as the late Cretaceous in a couple places, which is while the severe thrust belt still being built, which that's interesting. And then extension, I'm kind of blocking it with my orange box here, but extension in a number of ranges, either approximately coinciding with or slightly postdating the sweep of ignimbrite volcanism through eastern Nevada, and then extension everywhere in the upper crust from the Miocene to the present. In contrast, the magmatic arc, the other place where we had high magnitude extension way back here, we didn't get widespread extension starting until the Miocene, until about 20 MA in a lot of these ranges. So all of that high magnitude extension in Western Nevada was accomplished in the last 15 or 20 million years. So I think a more effective way to talk about the results of this graph is to talk about extension in the terms of chapters or episodes. And so here I want to kind of summarize everything. Nearly all the extension in the Basin and Range, I and others argue, could be related to a series of relatively punctuated geodynamic events that may have allowed extension to occur. If we look at the oldest event, we see evidence for, in just a few places, in fact, just 4 places that I highlight here, and this would have been in the high elevation Nevada Plano, we see evidence for localized, relatively low magnitude, spatially isolated, localized extension of late Cretaceous age, which again is going on while the severe thrust belt is still being built. So making it geodynamically pretty interesting. The one person that's put forth a model that's attempted to explain this in terms of orogenic wedge dynamics is Mike Wells at UNLV. He put forth an interesting model that delamination of mantle lithosphere underneath the retroarc caused a big dump of heat and an isostatic adjustment in the overlying wedge, resulting in localized extension. We could debate whether that model is correct or not, but that's the only model I know that's put forth an interesting mechanism to try to explain this in terms of what was going on in terms of intraplate forces at the time. So this was chapter 1, and this did not amount to that much east-west widening. Chapter 2 also did not amount to that much east-west widening at the province scale, but it was also very interesting. During the late Eocene to Oligocene sweep of volcanism across eastern Nevada, we do get evidence for still spatially localized, but much more widespread extension. In fact, this is a figure from a more recent paper of mine where I compiled about 50 plus localities where field relations for mid-tertiary extension have been presented. So it was distributed across a pretty big area of the Nevada Plano, but it was very heterogeneous in style and magnitude. Most of the places I highlight here are single normal fault systems that either had sediment associated with them, like little mini half grabens. But there are 3 fault systems that I'm really interested in here that in eastern Nevada that did accomplish much of their slip during the Oligocene. So it was distributed, very heterogeneous in style and magnitude. And again, it approximately corresponds in time with the sweep of volcanism across Nevada. And so several, including Bill Dickinson and Mike Smith and others that have thought about this for a while, have interpreted that this chapter or episode of extension may have been triggered by a change in boundary conditions, meaning a transition from the shallow geometry of the Farallon slab as the Laramide province was constructed to one that rolled back to a steeper geometry. And this would have resulted in a pretty significant decrease in the east-west distance of interplate coupling between these 2 plates. Incidentally, you could have also had trench retreat going on further outside too. In other words, we took this thick mountain belt and we made it a little bit unstable by rolling back the slab. Now, those were chapter 1 and chapter 2. They really pale in comparison to chapter 3, the big one. The one that gave us the basin and range that we know today, the one that gave us the awesome topography. And this was almost entirely during the Neogene, most of which in the last 17, 15, 20 million years, depending on where you look. So this is responsible for the majority of east-west widening, and this is where we got widespread upper crustal extension. And during the late stage of this is where we got our relatively evenly spaced valleys and mountain ranges that we know and love. So the ideas for the geodynamic trigger for this go clear back to a really pioneering idea by Tanya Atwater as far back as 1970, who first realized that the progressively increasing influence of and growth of the San Andreas fault system is really what's largely responsible. Because we went from a scenario of through-going subduction, where essentially the bulldozer is pushing toward the east the entire time, up and down the full western length of North America. But as soon as the Pacific plate made contact with the North American plate about 30 to 25 MA down here, that all started to change because as those triple points migrated north and south, we started to get the growth of the San Andreas transform at the Pacific North American boundary, having progressively increasing influence. In other words, we're seeing the demise of subduction and a complete change in the relative plate motion vector from one where the bulldozer is pushing to the east to one where the bulldozer is pushing laterally and perhaps even pulling gently toward the west. So there was this change in relative plate motion vector that allowed the thick crust of the Cordillera mountain belt to really extend for the first time. All right, that was a lot. So to wrap that up, just a few conclusions. It's been documented for a while that the extent of crust thickened during the Cordillera mountain building event was the dominant control on where we did and didn't get extension at this latitude. Bill Dickinson and others have been saying that for a while. So at a really big scale, gradients in gravitational potential energy, in other words, gradients in crustal thickness, where we had fat crust in the middle and thinner crust on either side, had to play a strong role and be an underlying really important driver. However, I think we can take this a step further, and I put forth an argument that variations in crustal thickness within the Cordilleran mountain belt itself may have actually been what controlled why we got a bunch of extension in some places in the Basin and Range versus very little in others. And then finally, it's been argued, right? So we see this, particularly in eastern Nevada, we see this history of extension that goes all the way back to about 75 MA locally. And so it's been proposed that the Basin Range really represents the protracted, unfettered gravitational spreading of thickened crust. But really, when we look at the timing record, I don't think this fits the data. Instead, almost all extension can be more temporally limited into more punctuated intervals of time that we can argue likely correspond with geodynamic driving events that triggered chapters or episodes of extension. And these driving events, it took the fundamental alteration of important boundary conditions, including largely changing the lithospheric density column and the strength of the orogenic wedge following late Cretaceous delamination, which perhaps triggered localized late Cretaceous extension. A decrease in interplay coupling accompanying the rollback of the Farallon slab during the mid-tertiary, which facilitated extension over a broad area of eastern Nevada, even though it still didn't amount to that much widening. And then finally, the really big event, the event that gave us the Basin Range that we know today, controlled by the reconfiguration of the Western North American plate boundary from one of through-going subduction to one of transtension. So that's all I have. I sincerely appreciate everyone listening, and I really wish I was able to come up and give this in person, but we'll have to do this again a year or two from now.
Yeah, everybody's clapping right now, Sean. I know. We have over 40 people showed up, so that's great.
Wow.
I guess should have probably fixed the Q&A button, but I was too fascinated by your talk. I was enjoying it so much. So if you guys do have questions, please do throw them in the chat menu, and we can ask Sean. Before we get going again, I know Sean teaches at Washington State University, and anybody that's listening, if you do have, are able to support your local geology department, please do consider. It's always a rough time for everybody. Sorry to throw that out there. I'm the chair of the geology department at Eastern, so I kind of have to stay there. But yeah, so Sharon from EWU actually asked if you did the minimum value of extension, is it possible to estimate the maximum value of extension? And have you done that?
No, that's it's a minimum because of the methods used, I guess. And so, the best I could do would be use the high end of the error estimate that I calculated. But like I said, in the absence of the ability to know more about what's going on underneath those basins where nothing's exposed, it makes it a challenging problem. So, I think the best I could do would be to add that 42-kilometer error estimate on, which accounts for some error in closing the basins and kind of the high estimate of offset on the Snake Range to Calmont. I think that's about as good as I can do with the methods that I use. Put it that way.
Fair enough. I got a lot of people saying thank you. Mark Hempel-Haley from Humboldt State University. I know the field camp. I went on that field camp out in the White Pine Range. Gorgeous place, like Sean said. So you did say the slab rollback, Nevada, pretty classic. When you come up to eastern Washington, northern Idaho, we also have these core complexes. And could you maybe mention a little bit about that? Are they the same process?
Oh, that's a good question. Yeah. So, and that's actually something I've been getting interested in since I've been up here. John Watkinson at WSU convinced me that I should take my structure field trip every year to the Kettle Dome. And I have been doing that, or at least I did up until a year ago. And now I go to the Salmon River. But Yeah, so there are nice domes, metamorphic core complexes. I think most people in this area most people that work in them in southern British Columbia, northeast Washington, call them nice domes, but I would call them core complexes. You do have areas of high magnitude extension in which you've brought mid-crustal rocks up to the surface. And I think that was done only about 50 million years ago at this latitude. So where you form these hinterland core complexes. One interesting difference is up here, they seem to be whenever we look at these exhumed rocks, they appear to have a lot of partial melt in them. And that's actually something like in the Snake Range Core Complex in Nevada, we don't see any partial melt at all. I think you had a thick origin that got very hot for some reason right around the early Eocene, and then underwent, as I understand it, a pretty rapid episode of east-west extension where you exhumed these mid-crustal rocks to the surface, and you had a really cool surface record of volcanism going on, like the grabens that are preserved up at Republic. So, it seems to be more punctuated in time, though, as I understand it, like 50 to 45 or 50 to 40. I mean, a lot of you guys probably know that better than me.
Yeah, I think you're right on 54. Yeah, we'll try to get Baldwin up here to give a talk.
I'd love to work up in the Kettle Dome and the Okanagan Dome. I think there's a lot of great stuff left to do up there for sure.
Well, you are welcome in Spokane. We've got some great stuff up here too.
Nice.
Nice. Yeah, I'm not sure. Oh, the Q&A. There we go. So why were the basins tucked to illustrate the geometry, says Benjamin?
Well, there's every one of these. If you go down across Highway 50, the range is all bedrock, but as soon as you enter the basins, it's no exposure whatsoever. It's entirely covered by quaternary sediments, and occasionally in areas that have been a little bit more complexity to form, sometimes you will pop up and expose some of the valley fill, mainly Miocene valley fill in those basins. And so sometimes you can work out a stratigraphy to it, but you rarely see the bottom. So there's no way to get at, there's really no easy way to get at the depth to the basal unconformity of the valley fill. And there's really no way to figure out how much normal faulting went on underneath that valley fill before these young basins opened. You can get at you can use geophysical tools like gravity modeling to attempt to estimate the how deep down the contact between Neogene valley fill and Paleozoic bedrock is. So, and sometimes you have the occasional drill hole that gets that deep, but you don't have enough cross-strike information in an individual valley to illustrate hardly anything in terms of how much it's been widened east-west. What you would need would be bedrock exposure at the surface.
That makes a lot of sense. Yeah, they are very dramatic topography. I mean, beautiful. It is getting late here. We had a great turnout today, Sean. That was an awesome talk. We have a recording of it. I'll try and share it with you. If it's okay with you, we can post on our website. We'll see.
Yeah, absolutely.
No worries either way. I really appreciate you taking the time. And if you can make it to Spokane post-COVID, let us know.
Definitely.
Great to talk about this structure.
Yeah, I would love to go to the bar and grill and do this in person. It'd be way more. It'd be awesome.
Nice. Yeah. And Blue Waters Bluegrass Festival with your band.
Yeah. Someday when it all comes back.
That's right. All right. So thank you very much, Sean. Have a great evening.
Thank you.
Thank your family too. Yeah.